This program is a presentation of UCTV for educational and non-commercial use only.
The Kavli Institute of Theoretical Physics at the University of California, Santa Barbara is the most important international scientific research center you've probably never heard of. Known in the physics community as KITP, the institute is nestled in a Michael Graves designed building 100 yards from a splendid stretch of the Pacific Ocean. With a small full-time faculty, KITP each year attracts 1,000 of the world's most innovative scientists to UCSB. They come for the chance to collaborate and study the most urgent questions in science about the nature of everything. The driving force of KITP is Dr. David Gross, its director and a world-renowned theoretical physicist.
One of the former visiting researchers said this about the Kavli Institute. Coming to Santa Barbara as a KITP scholar is like joining a brotherhood in a place of worship. To physicists, it is as Jerusalem is to the Jews or as Mecca is to Muslims, with David Gross as custodian of the holy shrine.
Oh, my God.
What is it about the Institute that would make a sober-minded hard science guy talk with such rapture?
Well, I must say I'm intrigued by the religious comparisons. When asked by my colleagues after I came here, what is it like to be a director? That must be awful. I said, no, being the director of the KITP is like being captain of the Love Boat. Everyone is happy. So I only have to deal with very happy people because scientists like to do science. And in many universities, they have to serve on committees and deal with students and other distractions, whereas we invite the order of 1,000 scientists a year to come and spend months, weeks here doing what they really love to do, which is talking about science and working on the frontiers of science with their colleagues. And they love it. And of course, they're in beautiful Santa Barbara, and we try to make it comfortable and encourage the interaction. So I think that's the origin of those remarks.
You said the Institute is expanding the horizons of physics. Where are the horizons of physics today?
We define physics very broadly, and many of the horizons are in the outlying areas which weren't traditionally the domain of physics. Physics is a very imperialistic effort. Physicists think, especially theorists like us, this is a theoretical institute, so we work with paper and pencil and blackboards and ideas. Theoretical physicists have accomplished much in the last few hundred years and feel they have very good methods that can be applied to problems they see in nature, whether they were traditionally called chemistry or biology or astronomy. So we define physics very broadly, and some of the frontiers are in areas like biology, where they face complex quantitative problems that physicists think they can contribute to. Other frontiers are in the core domain of physics, such as the search for the elementary particles of nature, the elementary laws of nature. So there are many frontiers, and often of different nature.
What are some of the fundamental questions that you're asking and trying to answer here, and why are they important?
There are questions about the early history of the universe. How did it all begin, and how did structure, galaxies, planets, emerge from the Big Bang? There are questions about the fundamental laws of physics. Can we unify all the forces together? Can we understand gravity? There are questions about the structure of quantum materials at the nanoscale. Can we use quantum mechanics to construct new computers? There are questions in biology, which our physicists are beginning to ask. Can we understand in a quantitative way and model evolution? Can we understand how the cell works and how the genetic code realizes its potential and makes life work? And then there are other, for example, we had last year a program on questions that concern us all, and even physicists who think they have something to contribute nowadays. What is the physics of climate change, and how can we use physics to improve our modeling, understanding, and maybe even control of the climate? There are so many questions.
And many of the questions have, very broad appeal, I think, as evidenced by the large turnouts when you have public lectures or other things. But how do you explain to people without advanced or any scientific training or knowledge of technical ideas what the heart of this science is?
It's not easy. The main stumbling block often in trying to convey the excitement we feel about the discoveries made in physics and our understanding that grows exponentially with time is that we describe the world in quantitative terms. The language of science, the language of nature, as Galileo said, is mathematics. And but many people their last encounter, often unpleasant, with mathematics was in high school, and they're afraid of mathematics. So from my experience, the real stumbling block is how to describe our mathematical understanding of the world in ways that don't scare people and don't require deep knowledge of mathematics. But when you succeed in doing so, I have found very few people who are not enormously interested in what the world is made out of, and how does your cell phone really work, and how did the universe begin, and how does life work. So the questions are ones that everyone is fascinated by. The answers, or the partial answers we have, fascinate people. The difficulty is to get rid of the jargon and the advanced math and explain it in simple terms.
And you just used the word art, and in talking about theoretical physics, there's often references to an elegant theory. That something's an elegant theory. What is the role of elegance in theoretical physics?
It's hard to define beauty, elegance, but it's one of these things you know when you see it. But you have to see it with mathematical eyes again. It's like hard for me to describe what it is. It's sort of like describing why do you find a Mozart symphony beautiful? How could you describe that to a deaf person? So it is a little difficult to describe the kind of mathematical beauty that a simple idea or equation can have in its ability to explain succinctly and adroitly and powerfully so many complex phenomena. There's something very beautiful about that, and that after a while becomes so this is an acquired taste of beauty, and often a good guide to trying to understand nature at a more profound level. For whatever reason, it has been the experience of science, and especially of physics over the last centuries, that when we truly understand something, the explanation, the equations, the theory is often exquisitely beautiful. So it's a good guide if you're working and you're on an idea that isn't beautiful and is ugly. It's probably not right either.
Well, I think when most lay people think about great research in physics, they always think about Albert Einstein at Princeton, or maybe Berkeley or Stanford. How has UCSB managed to build this institute, and where does it stand within the world of physics?
Well, the brilliance of the professors, the Gang of Four, as they're called in the UCSB physics department, 30 years ago, was to answer a call from the National Science Foundation to try to set up a National Theory Institute. The NSF didn't have a real idea what it was to be, but the Gang of Four had a winning proposal out of 50 proposals. Each state, more or less, had a proposal. And this is a lovely place, and a perfect setting for the idea that the way that what was really lacking worldwide was a place where people could come together from all over to attack important research problems together for prolonged times. And this model, so we really were the first. By now there are, believe me, dozens of places that try to emulate and imitate this setting. A few successfully. But it was a great model and a new innovation, and throughout its history, it has the ITP, the Institute for Theoretical Physics, was flexible enough to perfect that model, become more and more attractive, and to enlarge the scope of its activities in different areas. And the community of scientists throughout the world, I mean, we have, every year, we just compiled the number for a review, 22,500 visitor days. That's visitor days. One visitor, one day.
Mm-hmm.
Roughly 1,000 individuals every year coming from all over the world. So this is a place that, you know, is not just in fact, very little of what goes on here are people who live in Santa Barbara year-round. There are people who come from all over the world. This is the center, the nodal point for the meeting point.
So if the global reach of the Institute is one distinctive feature, its collaboration and interdisciplinary approaches is another. Mm-hmm. What are some examples of how that works from different perspectives and different disciplines?
We try often in two ways to encourage such cross-cultural, interdisciplinary research. Very difficult to do in ordinary universities that have constructed departments of physics, departments of biology, say. Now, often the questions that are posed by nature are in between. And every department says, that's my turf, and that's my turf, and they find it very difficult to cooperate. Santa Barbara in general, UCSB, has a marvelous tradition of interdisciplinary research, and one of the reasons I think the Institute as a whole was able to work so well in that domain was the tradition of UCSB. So one of our main goals is to try to break down those barriers. That's easy for us to do in a sense because we can bring people from both cultures together. And we have learned over the years that how to help different communities solve their language problems, talk to each other, work together. And there are many places where we've done that. Biology and physics is one of the most recent, but it goes back over the years, and in some cases leads to new fields. A great example has to do with the effort on quantum that is driven towards building a new kind of computer based on quantum mechanics, the quantum computer. This is a very long-term goal, but one that could revolutionize the way we process information using quantum mechanics. And that effort we stimulated very early on by bringing together people from different areas of physics to work on what originally was a pretty far-out idea. More recently, by bringing together people from atomic physics and condensed matter physics in workshops that were side by side, and then as they began to collaborate more closely on workshops directed towards their new field. So we're always on the lookout for such synergies, and we give an opportunity to do experiments in collaboration between different fields.
And when you talk about them speaking the same language, you're not speaking about different countries. You're talking about different disciplines and the different
Right.
scientific
As if I
disciplines.
started talking to you in mathematics, you might have a blank. It is true of every discipline in science, not to speak of, we talked before, difficulty of communicating to the public at large. There's equal difficulty for a biologist and a physicist to talk about how the cell works. Each subdiscipline tends to invent its own jargon, which other disciplines don't understand. They have very different approaches. And getting people from different disciplines, even within physics, to collaborate, to understand each other's approach, to talk to each other, is not easy, but is often necessary and enormously productive.
You've said that in science, discoveries don't happen in 5-year cycles, referring to the funding cycles of the National Science Foundation in this case. But one of the things the Institute, as I understand it, has tried to do is to focus on rapid response to scientific discoveries. Can you describe what that looks like?
Well, with some of the private money that I raised, we were able to fund programs that could respond within 6 months to a breakthrough. Typically, our programs have to be planned 1.5 to 2.5 years ahead of time. It's difficult to get people to disrupt their normal life and come out here and with or without family and teaching obligations. But science doesn't always develop that slowly, and there are often breakthroughs that occur, and usually in the laboratory, new observations, new discoveries, and theorists become, very excited and start producing lots of papers and want to talk to each other, and this is a perfect locale for that to happen. So we devised a new program called Rapid Response, where we could schedule a 2-week workshop bringing the experimenters and the theorists together if there was a development in some field. And we've had 5 or 6 of these already in the last few years, and they've been enormously successful because although I cannot predict what the discovery will be in the next year from now, I can predict there will be 1 or 2 in some field of physics, and we should be ready to rapidly respond.
In talking about collaboration, there's a lot of physical signs of that as you walk around the Institute. The blackboards that you see everywhere, and scientists talking to each other. Even the afternoon teas that you have in the courtyard where people talk.
If you start asking questions about like the dynamics of the clusters, so these are called percolation problems, and then you get something that actually in the space looks sort of not trivial. So the question is like,
as an administrator, as the person who runs the place, I mean, do you give attention to that level of detail? How am I going to facilitate this?
Sure. And we're trying all the time and extend. We went through a renovation of the building about 5 years ago, and part of the whole plan was to create more and more areas where people accidentally on purpose bump into each other and stand there in the corridor and have a blackboard nearby so they can start jotting down their thoughts. There's often I find a public perception of scientists as nerdy loners who sit in some laboratory poring over their pencil and paper or instruments and not interacting with anyone, not to speak of anyone of the opposite sex. And this is, believe me, on both accounts, far from the truth. Scientists are incredibly collaborative and interactive. They like nothing better than to talk to each other and tell the other person their crazy ideas and get feedback. It's partly because, and the ideas are so, one is not always sure of one's tentative, new, creative ideas, and getting that feedback is essential. And scientists are incredibly collaborative and interactive, which is why a place like this is both necessary and successful. So if you walk around, you'll see people talking all the time next to a blackboard, and some in the courtyard or one of the many centers we have, and that's how science actually works. It's a very interactive, collaborative, by and large, friendly activity.
You know, you have this baseball hat on one of your shelves here. It says, "Gross the strong force," which, of course, as we all know, is one of the four major forces of nature. Tell me the story of that hat. Where did that come from, and what is it a reference to?
December 2004, I went to Stockholm to get a Nobel Prize for figuring out how the strong or the nuclear force works. When you go to Stockholm, you get to invite members of your family and friends and so on. And I had about 19 people in my party. And my daughter, so I have 2 daughters and at that time 2 grandchildren and so on. My youngest daughter decided we needed some identification. So she made a baseball cap, which was entitled Gross, for the grosses, the strong force. And she insisted that we wear it on various occasions.
You won the Nobel Prize in 2004, as I understand it, for your research on quarks. What is it like to make a major scientific discovery, you know, to know something about the universe before anyone else does?
Well, yeah, that is one of the really neat feelings, to have this feeling that you really understand something basic before anyone else does. It lasts a few weeks because a lot of your, I mean, you know, you immediately you inform your colleagues, and some of them, or a small number of them, get it immediately. So the number of people who know something grows. As far as our discovery goes, the really crucial insight and use of that at a basic level happened rather rapidly and over a short period of time, so it was very exciting and scary as hell.
Why scary?
Scary because, you know, who knows whether this crazy idea, and there were many elements of it that to many people seemed preposterous and unlikely, was true. So it's scary because were it to be true, it would explain something that we'd been trying to understand for decades, and be a pretty big development, and with lots and lots of potential for understanding the interior of the nucleus and how the nuclear force works. But it could be false, and only nature can decide. And there were conceptual problems. How could it be true? It seemed. So it's always a mixture of anything. When you go out on the limb in a big way, you're out on the limb. And it's different when you're making a theoretical discovery because you have to wait then for nature through experiments, precise predictions, to test these ideas and prove them correct. And in our case, that took maybe 20 years to be definite. Whereas an experimenter is much luckier. If they discover something, you can just see it in the laboratory. Sometimes it's confusing and there are errors, but often it's just there. And you're sure of it immediately because you found something in nature. Whereas a theorist is trying to construct something which, as many people say, is just a theory.
So is there a eureka moment to that, the way that there would be an experiment?
In our case, which is somewhat unusual, there was a eureka week.
When it was all dawning on you that this was all falling into place?
When things worked out in such a way that we could have an explanation of very crucial experiments that dealt with the behavior of quarks, and that led to a very specific theory which could explain potentially so much more.
Let me ask you one more question. Are there limits to how much we can know about the universe?
Yeah, I'm often asked that when I give public lectures, especially when I talk about some of these very difficult problems like how did the universe begin? Maybe there are limits to what we can know, especially in those areas of fundamental physics. There are areas, by the way, of complex physics, the structure of ordinary matter or biological matter, that are very difficult. These are very complex systems in ordinary human cell. But we do understand the basic laws of physics and chemistry. We sort of have a feeling that those questions will be answered. It might take 50 years, but they will be answered. But what about the origin of the universe? It could be, some people argue, that it's just beyond our comprehension, just as quantum mechanics seems to be beyond the comprehension of my dogs. I've tried to explain it to them. They don't get it. And I don't think they can. Their brain is simply, is our brain limited? So I answer that by saying, maybe not. Chomsky always argued that language had infinite capability. A newborn baby could explain, could utter new sentences that no one had ever learned before, uttered before. So we might have some kind of, it's not clear what the limits of human intelligence, consciousness are, mathematics. But then I also say, we don't know the answer to that question. Neither do my dogs really understand that they don't understand, but there's an experimental test. I think if we were getting to the point where we were beginning to get close to the limits of our capabilities, we would start noticing that young students beginning to learn a subject like physics or mathematics would take longer and longer to get to the point where they could make contributions. It's like climbing an ever and ever steeper mountain. You'd begin to notice it. And that's not the case. I mean, it's still the case that brilliant minds can, by the early 20s, have learned enough of everything that we've learned over the last few hundred years and be ready to start going strong and continue to make increasing progress. So I see no sign that we're nearing impossible questions, nearing the limits of our capabilities. It might be the case, but there's no evidence of that yet.
Well, Dr. David Gross, thank you so much for talking with us.
It was a pleasure. Thank you.